Good day, everybody. This is Mr. Reynolds, and this is our final lesson for the year. It is a very sad circumstance we find ourselves in, but we're going to finish with a bang. We're going to be talking about Feynman diagrams. Now, those of y'all that joined us for our Zoom chats on Wednesday and Thursday on the 22nd, the 23rd of April, this is pretty much what you heard me talk about. I'm putting this forth for you in order to help you review, and for those that maybe didn't get a chance to listen and didn't get a chance to tune in because of whatever reason. So let's talk about what a Feynman diagram is. A Feynman diagram describes the interaction between two fundamental particles. So whenever you have a quark or a lepton or whatever, and those two interact in some way, they hit each other, they fly apart from each other, they do whatever. There's some interaction, change from one to another maybe. You can describe the interaction with Feynman diagrams. Now, the nice thing about a Feynman diagram is they're pretty simple to understand if they're valid or not. Like, you could literally teach your younger sibling in probably 5 minutes to be able to look at a Feynman diagram and identify, is this valid or is it not? And the cool thing is, if you can draw an interaction with a Feynman diagram that is valid, that is something that could happen. It may not be hugely likely to happen. It depends on a lot of other things that we're not going to consider. But if you can draw it, it could happen. Now, there are really two parts to a standard model. We have the boson. The boson, in the real world, standard models use different types of lines for bosons, so maybe a dash line or a loopy line. We are simply going to use a line like this, just to keep things simple. All bosons, we use that kind of line. And then we're also going to have the fermions. A fermion, that could be a lepton or a quark. And they're going to be represented by an arrow. Now, there's two types of arrows. An arrow forward in time, that is a standard particle. So your standard up quark is drawn with an arrow moving forward in time. A anti-particle, so let's say an anti-up or an anti-electron or an anti-neutrino, is drawn backwards in time. That does not mean that anti-particles are time travelers. It doesn't mean that they are, breaking this time-space continuum, whatever. It just simply means we draw them backwards in time. And so let's draw our first simple Feynman diagram. Let's look at a real physical situation. This is a situation we talked about in our last video. We talked about earlier in class. We have two electrons, and these two electrons are moving towards each other. Now, as these two electrons move towards each other, they are going to be repelled. And they're going to be repelled from each other because they have the same charge. There's an electrical force between the two of them pushing each other away. They're going to get closer and closer and closer, and then at some point they're going to turn around and rebound away. Okay, the top one will do the same thing. And that's all well and good in the electrical chapter, but what we want to focus on is really what's going on behind the scenes. How does the top electron know that the bottom electron is getting closer? We can do this using a Feynman diagram. So let's start with two electrons. Now in our Feynman diagram, we need to define our axes. Our y-axis here is simply a position vector. So the closer these two electrons are to each other, the closer they are in space. We will have time on the x-axis. Now, you're not going to find consensus everywhere. A lot of times Feynman diagrams are written with time going up. In IB, typically we draw them with time going to the right, but you also see them time going up. But, whatever, you're smart. You can figure it out. Now, these two electrons, they are going to move towards each other. Now, we're going to draw them moving towards each other with these diagonals. The diagonals do not mean they are moving at some angle. What they simply mean is their position between them is decreasing as time moves on. At some point, the bottom electron will give off a photon, and that photon, or the boson, which is a photon in this case, will hit the top electron. Now, that top electron, when the photon hits it, it's going to, according to the law of conservation momentum, move away. And the bottom electron, when it gives up a photon, which does have momentum, it will also move away. This is a scenario where a photon from the bottom electron pushes the top electron away, and in doing so also pushes the bottom electron down. This is a Feynman diagram. We have our leptons here and our boson. Now, I had some people ask a question. Hey, well, what about that top electron? Doesn't the top electron give off a boson and push the bottom electron away? The answer is yes. This is not the only scenario that happens. In fact, you could invent all kinds of other scenarios following the rules of Feynman diagrams, which we're going to talk about in just a second, and they're all totally valid. But this is one possible solution. Now, in order to analyze this, to make sure we're doing okay, we're going to use the conservation laws we talked about the other day. So I'm going to look at 3 times. We're going to call these times time A, time B, and time C. And at all 3 of these times, everything, momentum, energy, charge, lepton number, boson number, must be conserved. So let's look at those. Let's see. We have charge. We have, let's change colors here. We have lepton number. And we have boson number. Okay. So first of all, charge. Using my standard model, I know the charge of this top electron is a -1. The charge of the bottom electron is a -1. That gives us a total charge of -2. The lepton number of an electron is +1. Electron is +1. Lepton number is +2. The baryon number, no, this is not a quark, so 0. This is not a quark, so 0. Baryon number is 0. These values, charge, lepton number, baryon number, they must stay constant the whole time. At times B and C, you must have the same values. So let's check it out. Let's see, charge at time B. Well, let's see, the charge of an electron is -1. The charge of this bottom electron is -1. So what must be the charge of that boson? Well, we're already at a charge of -2, which is what we want. So the charge of the boson must be a 0. Let's not use the eraser there. Must be a 0. All right, lepton number. Well, let's see. Electron, still +1. Electron, still... Oh, why do I keep switching? Still +1. And so that boson must not have a lepton number, which is good because bosons can never have lepton numbers. Also, baryon number. Well, still not a baryon, or still not a quark, still not a quark, and still not a quark. So all the numbers balance out. And if you follow it through, times C is exactly the same. All those conservation laws we talked about last week still apply. So conservation laws are one thing you got to pay attention to in a Feynman diagram, but the other is a simpler thing, are the 3 requirements for a vertex. Okay, what do I mean by vertex? A vertex is right here. A vertex is right here. The vertex is any time you have an interaction. Anytime something is happening. Anytime a lepton or a quark and a boson are interacting in some way. Now, every vertex, I don't care how complicated the Feynman diagram is, every vertex must have 3 things, and 3 things only. Number 1, must have a boson. Can have 1 boson, not 2, not 3, not 4, 1 boson. Every vertex must have an arrow pointing away. Now, I don't care what direction time is or anything, but it must have an arrow pointing away from the vertex. Finally, number 3, you must have an arrow pointing in to the vertex. So let's test this out. Here's our vertex right here. We have a boson. Boson's down here. We have an arrow coming in and an arrow going away. So that is a totally valid vertex. Same thing down here. Arrow coming in, arrow going away, and a boson. Totally valid vertex. As long as you're drawing your vertexes correctly and you're following the conservation laws, 2 things which I think we can do, you have a valid Feynman diagram. This is an interaction that can occur. What's wrong with this diagram? Right? You cannot have 2 bosons. You must have a boson, an out, and an in. Can't work. We have a situation like this. Again, you must have an out, an in, and a boson. Here we have 2 outs. Can't do that. Wrong. Can't do it. These are the requirements for a Feynman diagram. Now I want to look at 3 specific Feynman diagrams and analyze them with you. 2 of them are new and 1 is an old favorite that we've had in the past. So let's look at it. Let's look at this one. This is called pair production. Pair production. Well, we have a simple little photon. This photon's hanging around. It's moving through space. It's doing its own thing. Who cares? Again, time is going to move to the right. But at some point, we're going to have an electron fly out and an anti-electron. Remember, to make an antiparticle, we put a bar on top, and we have our arrow pointing backwards. Now, this is a valid vertex. We have a boson, we have an out, and we have an in. So that is totally valid. If I check my values for charge and all this stuff, this is a photon. So the charge is 0 on the left. On the right, we have a -1 and a +1, 0 charge. Lepton number 0 on the left. Lepton number 0 on the right. We have a +1 and a -1. For baryon number, 0 and 0, there are no quarks. So for pair production, this is a valid Feynman diagram. And this actually does happen, where a photon just chilling out, zooming through space, and it spontaneously creates an electron and an anti-electron. Now, an electron and an anti-electron, they are not going to like being next to each other. They have an opposite charge. They're going to attract each other. And so shortly after, time moves on, we have our electron and our anti-electron that we just made. And what's going to happen is they're going to attract each other. And they're going to annihilate each other. This is a process called annihilation. Maybe that's spelled right. Who knows? Wonders never cease. In annihilation, we have a total charge of -1 +1, so total charge is 0. Total charge is 0. For lepton number, we have a +1, a -1, which is 0, and 0 here. For baryon number, 0, 0, 0. And so this is an example of how a photon can create an electron-anti-electron pair, and they immediately annihilate each other. Normally we would write this like this. So we would do something like this. Here's the electron, here's the anti-electron. Happens very quickly, but it does happen. If that photon has enough energy, it can, using E=mc², convert that energy into mass, and it can create an electron-anti-electron pair. That's an example of Feynman diagrams. Again, just follows the rules, follows our conservation rules, and follows the rules for vertex. Finally, I want to discuss beta minus decay. Beta minus decay. And we could do this with beta plus decay. It's not too much more difficult, but beta minus decay, if you remember, has where you take a neutron inside of a nucleus, and you turn that neutron into a proton, plus a beta particle, which is just an electron, plus something else. If you can't remember that something else, we're going to sort of derive what that thing is. So a neutron, remember we start a neutron with an up, a down, and a down quark. Proton is out here on the right. That's an up, and a down quark. Now, the top two quarks, the up and the down, they don't really do anything. They just sort of hang out. They chill. All the interaction, this whole beta minus decay is really a decay of a down quark turning into an up quark. All this radiation given off by beta minus decay is the down quark turning into an up quark. So let's go through and write out what this thing is. So first I know the down quark, which is a standard particle, moves forward in time, turns into an up quark, standard particle moves forward in time. No problem. But what happens is, in order to make this Feynman diagram proper, we need a boson given off. We're going to talk about the identity of that boson here in just a second. Now that boson doesn't just end up moving through space. That boson then creates a electron and something else. Again, what is that something else? We'll talk about it in just a moment. Let's look at our 3 periods of time right here. We'll call these A, B, and C. And let's follow our conservation laws. So, first thing with conservation laws, we have charge, we have baryon number, and we have lepton number. Let's start with charge. Charge of an up quark, according to our standard model, is a plus 2/3. The down quark is a minus 1/3, and the down quark is a minus 1/3. That gives us a total charge, if you add up those 3 charges, of 0. That makes sense. A neutron should have 0 charge. Okay, no problem. Baryon number. Well, let's see. Baryon number for an up quark is plus 1/3, plus 1/3 for down, plus 1/3 for down. Total baryon number is a 1. Lepton number, well, up's not a lepton, down's not a lepton, down's not a lepton. Total lepton number of 0. These values, 0, 1, and 0, they must be the same at any other time that I pick. Any time in this interaction, in this scenario, you must have a charge of 0, baryon number of 1, and a lepton number of 0. It's got to happen. So knowing that, let's look at time B. Let's look at charge first. Charge will get you a long way usually. If you work out the charge stuff, you're going to do most things. So let's see. As charge and up is plus 2/3, just like before. The down is still minus 1/3. And now we have an up quark right here. Well, that's a plus 2/3. Now, 2/3 plus negative 1/3 plus 2/3 gives us 1, which of course is the charge of a proton. The charge needs to be a 0. Well, there's only one thing left to have a charge. So what must the charge of this boson be? Well, the charge, if we have plus 1 so far, needing 0, our charge must be a minus 1. Now that helps us a lot, because I know the only the only boson with a charge is the W minus boson. And therefore, this interaction is governed by the weak interaction, because the W minus mediates the weak force. And so we have a situation where the this beta minus decay, it all happens because of that mysterious weak force. Baryon number, let's check that. We have plus 1/3, plus 1/3, plus 1/3. Boson is not a quark, so we're still a 1. We're still good there. Lepton number, well, none of these are leptons, so we're still 0. We're still good there. So at time B, we are good to go. And we have actually identified what boson does this. It's a W-. Now let's check at time C. We'll go through the same stuff. Charge, plus 2/3, minus 1/3, plus 2/3. It gives off an electron. That's a minus 1 charge. So we have 2/3, minus 1/3, plus 2/3, minus 1. What is the total charge of all that? Well, the total charge is 0. We need a charge of 0, so this bottom thing must have a charge of 0. Must have a charge of 0 in order for the law of conservation of charge to stay constant. Let's check baryon number. Up is still 1/3. Down is still 1/3. Up is still 1/3. The electron does not have a baryon number because it's a lepton. And so we need a baryon number of 1. So far we have a baryon number of 1. So what must be the baryon number of the bottom thing? Well, of course it needs to be a 0. Okay, so this bottom thing cannot be a quark. I also know it can't be a quark because no quark has 0 charge. So there's another thing. By the way, you'll notice the only things with no charge are neutrinos. So I'm guessing it's one of the neutrinos. We always are going to default to the smallest neutrino, which is the electron neutrino, because anything bigger than that will typically decay into an electron neutrino very quickly. Finally, let's look at lepton number. No lepton number, no lepton number, no lepton number. The electron, however, does have a lepton number. Its lepton number is plus 1. I'm getting all of this from the standard model or section 7.3 in your data booklet. Well, let's see. The total lepton number must be 0. So far, we have a lepton number of plus 1. So my last thing must have a lepton number of minus 1. Well, what has no charge, minus 1 lepton number? Well, that's going to obviously be an anti-neutrino, typically an anti-electron neutrino. How will we draw that? Well, an antiparticle moves backwards in times, and look at our vertex. Now this bottom vertex does work. We have a line going out, a line coming in, and a boson. Same thing up here, line coming in, line going out, and a boson. This is the beta minus decay Feynman diagram for beta minus decay. Now, it looks complicated, but if you follow the individual steps, you can understand this. The assignment for this week is just going to be a worksheet where you look at a couple of Feynman diagrams, identify some problems, and identify some bosons, and answer some questions and stuff like that. This will be the final assignment for you for this year. So I hope this makes some sense. Please let me know if you have any questions. Remember, our Zoom meeting this week we will be having a bit of a party. So get you a cake, get you some unhealthy food. We'll have a little party. We'll reminisce about the old days of physics and wrap up our 2 years this next week. So look forward to seeing you then. I hope everybody shows up for that. Hope you all have a good day. It's Mr. Reynolds. Farewell.